Hello everybody, my name is Ho Kyung Sean at Center for Technology in Water and Wastewater, University of Technology, Sydney. This is my great pleasure to be part of this webinar series. I'd like to thank Professor Hyun-Suk Oh and organizing members in Seoul National University of Science and Technology. My talk today is energy efficient seawater desalination, current status, and future perspectives. I will start with a brief introduction of research group and research center and university. Then general information will be provided with water stress and desalination, followed by Australian desalination plants. How much energy do reverse osmosis desalination plants consume in terms of potential and pretreatment, reverse osmosis, and post-treatment? Then I will present how to save energy and to operate energy efficient desalination plants. This is our university. So we have higher degree research student, postgraduate coursework, almost 14,000 students. Undergraduate students are 30,000. So we have almost 45,600 students in our university. Our university is located in the middle of Sydney City, and you can see this is our Faculty of Engineering. So our center and school is located in this building. So you can visit to us when you have time to visit to Sydney. You are very much welcome to come to our university. And this is the science building, and this is our university library, and this is our Faculty of Business. So we have a very iconic building in our university because we have very much located in the city, so that we have very well balanced building with the high story building. Our center is collaborating with the government, industry, and community to address the complex water sustainability challenges through transdisciplinary research. So we consist of 20 staff, 60 PhD students. So as you can be seen, we have many different types of research opportunity. For example, we just have smart water cities building and climate change adaptation, energy efficient futures and landscapes and ecosystem, resource futures and water futures, water catchment management, and learning change, international development, water for food. In particular, my group is very much working on smart water cities and buildings, and energy efficient futures and resource futures, water futures, which is to develop the sustainable and resilient water management solution. Also, we are very much focused on energy efficient desalination, wastewater reuse, and technology development to accelerate the transition to more decentralized energy systems that are clean, affordable, reliable, and communities. So I just want to show my brief research activity based on this one. So we uh, prepare some membrane fabrication of membrane distillation, reverse osmosis, nanofiltration, organic solvent nanofiltration, pressure retarded osmosis, and how we can achieve the high performance membrane for water reuse and desalination. We have utilized electrospinning, um, inkjet printing, 3D printing, and flat sheet casting method, and hollow fiber spinnery. Especially the drop on demand inkjet printing is a promising approach, allowing the patterning of materials with negligible material waste. Hence, the significant reduction of raw materials cost can be achieved. Furthermore, inkjet printing can be easily adapted to a roll-to-roll process, which is suitable for large-scale application. And therefore, we try to incorporate some of the nanoparticles and then some of functional material and polymers to improve the overall membrane performance and to reduce the membrane fouling. So you can see all the method. We also try to incorporate some of nanomaterials to achieve the better performance, and then we produce the different kinds of membrane for water and organic solvent. Also, we have developed nutrient recovery, and which called resource recovery from urine and wastewater. So nowadays, due to the increasing population and industry, so we have used a lot of nutrient for food production. And when you produce the food, so we spend a lot of energy from the Haber-Bosch process. And then we have a limited reservoir of the phosphorus. So nitrogen, phosphorus can be a main nutrient to grow your food. And then we consume this food to discharge our nutrient to wastewater treatment plant. Also, you utilize a lot of energy to reduce the nitrogen phosphorus, so that this is the way of the linear economy system to produce your nutrient, grow your food, and then discharge your wastewater. And finally, in your nutrient, you discharge to the waterways such as rivers and lakes and the seawater, which will give nutrification. So that we need to make sure circular economy of the nutrient, and therefore we try to develop the urine nutrient recovery, because the most of nitrogen phosphorus contained from our urine, so that we have our urine harvesting tank in our toilet. So this is our faculty of engineering in our university, and male urinal. So we have connected this urine collection, and then we produced our urine and go through the membrane bioreactor system to make urine to nitrification and produce the ammonia and nitrate, which are the most stable nutrient in water condition. And then we utilize the distillation to concentrate our urine, and then we have nutrient, so nitrogen, phosphorus, and ammonia based nutrient can be applied to grow some of our crops and the plants. So we have developed a new product which called oval, which can be used for the circular economy system to recover our nutrient from urine. So we have developed membrane for membrane bioreactor, also membrane distillation to further concentrate our urine, and then we have operated for last several years for this resource recovery from urine. Also, we have developed the lithium recovery from seawater and lake water. As you know, lithium in Australia, we are the second largest reservoir we have for this lithium mining, and we want to further develop this lithium recovery from seawater, RO brine, and salt lake, because the lithium elements will be needed more for our battery application. So this is our one of the technology we have used capacitive deionization to recover urine. In particular, we have developed our ion exchange membrane, so lithium can selectively absorb in our electrodes, and then this electrodes we have developed some lithium selective membrane using HMO, H2, TiO4, COF, and MOF, and then we have selective lithium recovery by removing all the sodium, chloride, magnesium compound. So that's our overall research activities. Water stress and desalination. The number of the people living in water-stressed countries will increase from about 700 million today to more than 3 billion by 2025. Climate change worsens water stress in several ways, such as droughts and floods. So let's look at these world maps. You can see the more than 40% of water withdrawal as a percentage of total available water, and from 40% to 20%, the yellow color. So you can see this kind of color in Africa area. You can see the less than 10%, or from 20% to 10%. So this color is changed significantly in 2025, and this will be accelerated because of the unpredictable climate change, also our population growth, and therefore we need alternative water resources such as desalination are very important in the future. Let's look at the desalination. What's the current status? Seawater and brackish water are generally desalinated using two types of processes: thermal evaporation and reverse osmosis membrane process. So you can see the global SWRO capacity. Nowadays, the evaporation is less likely operated because of more energy consumption. And on the other hand, the seawater reverse osmosis is the most dominant market for desalination. So you can see the world mapping for different desalination capacity. So Saudi Arabia is the largest desalination capacity, followed by United States, Arab Emirates, also Asian country, Australia. So it's keep increasing the needs of desalination plants. So let's look at what's the capital cost. This is the capital expenditure forecast by plant type. As you can be seen, this is the 2013 to 2022. So $1 million of the value to $2,000 million, $10,000 million in terms of PWRO and SWRO and thermal treatment process. So you can see the capital expenditure of the thermal treatment process is very much stable compared to seawater reverse osmosis. So seawater reverse osmosis is becoming more dominant technology for seawater desalination. So let's look at the why it's becoming more dominant because of operating and maintenance cost. So you can see that the OPEX of the summer evaporation method has not changed much for last 20 years. And then OPEX cost of reverse osmosis, yeah, it's continuously increasing, and because there are more SWRO plants are made, and we need more operating cost. So you can see the overall $2,000 million for evaporation method, and this is almost $6,000 million for operation cost of SWRO and then PWRO. So this SWRO also created a lot of CO2 production, 2 kilograms CO2 per 1 cubic meter of the desalinated water. So total emission of desalination would be 120 million tons CO2 per year. Also, if you see how we can separate the variable cost and then fixed cost. So you can see the fixed cost include indirect monitoring, maintenance, and labor cost, almost 30% of the desalination process require. And then variable cost includes energy, chemicals, membrane replacement, waste stream disposal, which are almost 70%. The portion required for the variable cost. Among them, the energy cost is the largest, 51%. Therefore, we need the energy efficient desalination. Let us look at desalination plant in Australia. So this section will cover how Australian desalination plants were initiated, have been evolved, and will be transformed to an energy efficient desalination plant. Let's look at the desalination and water history in Australia. So we focused on last 200 years. Initially, so 1788. So we started from the tanker stream and the bores. And then nowadays we have many different kinds of water alternatives, and in the future. So if you look at this red bar, and this shows the very severe drought timing. So whenever we have severe drought and people realized, okay, water cannot be stored, and then we should have make some reservoir system. That's the reason why they created some dams or reservoirs. Also they have another dams. So we see all the dam development early 1900, and then we just utilized also different kinds of water resource because of the population and industry for the climate change. So you remember the 2000 Sydney Olympic Park. At that time, they utilized the wastewater reuse plant, and then still, yeah, for last 20 years. So we have operated the wastewater recycling plant, which very effectively, and then they realized also another millennium drought from 2010 to 2000 period, and that time we had 21 dams, 11 water filtration plants, 12 water recycling plants. However, because of the environmental issue and then water ecosystem, so we were not able to develop the more dams. And then we found out what's the best alternative water resource, and then recycling plant, stormwater, rainwater, and desalinated water have been our target water resource since 2010. So we have a lot of alternative water resource, Sydney desalination plant, water recycling, stormwater project, and then that's the way we have developed the desalination plant for last almost 20 years because of very severe drought. So if you see this Sydney desalination plant, so this is the water capacity of the full operation storage. So this is the dam in Sydney area, and then level of dam you can see 2000 they started decrease, and then this is the 50% level of the dam, and then they realized, okay, if we have one more drought season, and we would have a very severe water shortage problem. That's the reason why they started to build in 2008 for Sydney desalination plant. So this is the almost 250 million liter per day, almost $2.5 billion. So it started to operate January 2010, and then after we built one desalination plant, so rainfall increased. So you can see the keep increasing, and then almost fully loaded in 2012. That's the reason why the desalination plant was shut down June 2012. And the operation planning we have made the operate 70% dam level. We start reoperate, and then 2019. So we had another severe drought, and then we operate partially, and nowadays also we completely shut down because of the enough dam storages. So that's the reason. This is the one of history of the desalination. Even though we control operational, not operational, depending on our dam level, that we have very reliable the water insurance. This fantastic water insurance for desalination plant will secure our water resource in the future, because Sydney population will grow, industry as well. Also, another drought may come very soon, so that we don't have to worry about our water problem in the future in Sydney City. So that's the history of the desalination plant in Australia. And let's look at what's the difference of the 6 desalination plant in Australia. So during the Millennium Drought 2000 to 2010, so most of desalination plant was generated, and first one, Gold Coast Desalination Plant. Second one is the Sydney Desalination Plant. Third one is the Melbourne Desalination Plant, Victoria, Adelaide Desalination Plant, and Perth Desalination Plant, Southern Seawater Desalination Plant. So we have 6 main desalination plants. Most of them were built in 2005 to 2010. However, in Perth, Western Australia area has been always the drought season for last 100 years. So this Perth desalination plant was made in 1990s. So they had recently made another desalination. This is the 100-kilometer distance, because this area is especially very much dry area. So we have 2 desalination plants in Western Australia. So each state, they have a very big desalination plant. Let's see more detail. They are all renewable energy certificates obtained, because the energy is the big issue in a desalination plant. That's the reason why always the people worry about too much CO2 emission and the CO2 footprint, and then we need to do something for this desalination plant. That's the reason why the government, when they make this desalination plant, they connect with the renewable energy. So mostly they have been operated by wind farms. So if you look at the Gold Coast Desalination Plant, so reverse osmosis to produce drinking water for this area, and then they have drum screening as a pretreatment, dual media filtration, and then SWRO, and then CO2 remineralization. So the seawater was not converted into drinking water, is returned to the ocean through an underground pipe. 200 meter long diffuser system releases the water in an area about the size of the 8 football fields. And this is the Sydney desalination. They produced 200 million liter per day, which is the 250,000 cubic meter per day. Site covers 45 hectares and is located on the coast of Cornell, 25 kilometers from Sydney Central Business District. So when you have airplane to come to Australia, so when you land, so you can see the desalination plant, because this desalination is very much close to Sydney Airport, and the process is very similar. Drum screens, dual media, and SWRO, lime fluoride, and CO2 remineralization. Because this Gold Coast Sydney desalination plant have been operated by Veolia, same company. That's the reason why they have same process. Dual media filter, SWRO. The difference is pretreatment, lime fluoride, and CO2 remineralization is a little bit different from the only CO2 remineralization in Gold Coast. So they put more lime and then fluoride which can prevent the teeth cavity for this fluoride compound. Victoria Melbourne is one of the biggest renewable energy operated desalination plant, 440 million liters per day, and they have a very much similar process, your media filter, SWRO, line, and CO2 demineralization. Adelaide desalination plant, 300 megaliters per day, and as you can be seen, also they have some of screening system, also ultrafiltration, second pass SWRO system, and the lime and CO2 demineralization, post desalination plant, as you can be seen, dual media filter, and second pass SWRO, lime and CO2 demineralization, and this one has 140 megaliter per day, and near around 100 kilometer distance, the southern seawater desalination plant located. So this desalination plant use ultrafiltration and SWRO, lime and CO2 remineralization, which produces around 300 megaliter per day. So difference between this 6 desalination plant, so mostly they are very much same for SWRO. So they organized all SWRO for main desalination technology, and a little bit of difference for pretreatment. One is ultrafiltration, the other one is dual media filtration. Also, a little bit of difference of post-treatment. Some place they just utilize the CO2 remineralization. Some place lime and CO2 remineralization, and some other place incorporate lime, fluoride, and CO2 remineralization. If I summarize all 6 desalination plants, so you can see how this plant different. So most of seawater quality in terms of total dissolved solid, so they are very much similar, 36,000 milligram per liter. So product water, which is the drinking water quality less than 200 milligram per liter, they want to produce, and temperature is 20 to 15 degree, capacity 150 to maximum 450 cubic meter per day, and then they utilize the RO configuration, partial two pass, advanced split pass, and partial two pass, and then split pass, single pass, and then partial two passes. So this specific terminology is very much relevant to first pass, second pass. So first pass, I will talk to you later. To improve the water quality, they utilize the first RO and second RO permeate. That's the reason why they can partially combine with the first pass permeate to the second pass RO, or just completely they combine together. So that can be differentiate partial pass, partial split pass. So that's the little bit of different. Also two-stage BWRO utilize, most of them they utilize two-stage first RO and then BWRO system, and then RO recovery 45% in first pass, second pass, because already RO permeate has a very low TDS, so they utilize around 90% BWRO recovery. So energy recovery device. So we have two types of energy recovery device. So if you look at the Perth Adelaide Southern Desalination Plant, they utilize pressure exchanger. And Sydney, Gold Coast, Melbourne, they utilize the dual water exchanger energy recovery device. So this energy recovery device, they have their own advantage, disadvantage. Nowadays, the pressure exchange, the overall efficiency is better than dual exchange water recovery. So people are utilizing mostly pressure exchanger, and then this is the mostly recommendable. So they try to recover energy almost 90%, and then this specific energy consumption total is 3.6 to 4.2 kilowatt hour per cubic meter. RO system only can consume 2.4, 2.9, 2.9 kilowatt hour per cubic meter. So why this RO is a little bit of difference? Because of the water quality issue, different pretreatment, so that they would have different energy consumption. So this is the all 6 desalination plant in Australia. So we have developed, and then we utilized this desalination plant. However, nowadays in Australia we have enough rainfall. That's the reason why only 2 desalination plants are mainly under operation in Western Australia. So you can see the Southern and then Perth desalination plant, because they have not much raining, but most of the area, Adelaide, Sydney, Gold Coast, Melbourne, they have enough this rainfall. That's the reason why they can make good water management, so that they have shut down this desalination plant whenever they have enough rainfall. Also, when they decrease their dam level, and then they can improve their own desalination plant process and reoperate, and then produce the alternative water resource. So that's the way we have operated the SWRO desalination plant. This section will cover the history of SWRO and energy distributions in terms of pretreatment, RO, and post-treatment. Then we will discuss how to save energy and how to achieve this kind of strategies. So let's look at the brief history of SWRO. 1956, the first seawater desalination plant in Kuwait and desalination commercial plant construction were made 1970, and 1990, so 2000 until then. So we have a first generation of RO. At that time, the energy consumption of RO was around 10 kilowatt hour per cubic meter. And then distillation was the leading technology, because the energy consumption is very much similar to RO, and then distillation. Distillation is better a little bit. And then RO technology innovation, also optimization, has led to the more RO technology is superior, and then try to make a more leading desalination market using SWRO from 2000 to 2010 because of development of energy recovery device. So we have operated the seawater desalination up to energy consumption 4 kilowatt hour per cubic meter. So this is the how we innovate the reverse osmosis. First one was membranes, modularization, and process. And second one is the more energy recovery device. So second generation of innovation have been evolved for SWRO technology. So if you look at the detailed energy distribution, so you can see the intake around 0.2 kilowatt hour per cubic meter, and pretreatment 10% of the energy consumption 0.4 kilowatt hour per cubic meters, and reverse osmosis almost 72%, 2.8 kilowatt hour per cubic meter, and the other facilities 0.2 kilowatt hour per cubic meter, and then water delivery service 8%, 0.3 kilowatt hour per cubic meter. When you consider your water quality 35,000 milligram per liter 23 degree, so it has 3.9 kilowatt hour per cubic meter in general seawater reverse osmosis process. If we look at the energy, so SWRO system 31%, power 26%, so intake, discharge 11%, pretreatment construction 12%, so project design and permitting 7%, SWRO replacement 6%, others 9%. So if you look at all the cost of desalination plant, so if you see power 26%, so we have to understand first what's the kilowatt hour per cubic meter. So when you consider 10 watt light bulb and 10 hours, and we have 1 kilowatt hour. So in other words, you have 10 light bulbs and then 1 hour, so which means 10 times 100 watts, 1000 watts for 1 hour is around 1 kilowatt hour, which is very much energy intensive when you consider 4 kilowatt hour per cubic meter for desalination, which means you can operate 40 light bulbs 100 watts for 1 hour when you produce the 1 cubic meter of the seawater to desalinated water. So when you look at the more detailed cost comparison, in Australia we have $0.25 per 1 kilowatt hour. So capacity is 200,000 cubic meter per day desalination plant with 4 kilowatt hour per cubic meter energy consumption. So energy cost is almost every day more than $200,000. Therefore, when you consider 1 year, so how much you need to think about your operating cost, multi-million dollar required to produce the desalinated water. So that we need to look at how to save energy. 1 kilowatt hour energy will save a lot of cost. So 2.8 kilowatt hour in RO is the most abundant energy consumption. Therefore, we can consider RO first. How can save your energy in RO system? Also, we will go for next step, pretreatment, post-treatment, one by one, how much we can possibly save using advanced technologies. So let's just see evolution of RO permeability. The initially RO membrane was made from cellulose acetate. First generation of the RO membrane in 1970, Sydney Law and Dow Chemical, they developed the thin composite, the polyamide reverse osmosis membrane, which has been improved a lot of water permeability, and also nano composite TFC membrane reverse osmosis has been developed. Also in the future 2020 we also look at some biomimetic membrane, aquaporin, graphene, carbon nanotube can possibly play a role to improve the overall RO membrane permeability. So every 15 years it has been doubled, this reverse osmosis membrane. So in the future we believe RO still there are room to improve the overall permeability. So if you look at the thin film composite RO membrane, currently commercially available RO membranes are mostly based on the thin film composite polyamide RO membrane. So it's better to understand how they have been produced. So chemistry of TFC RO membrane active layer, we utilize the polyamide layer in situ condensation of polymerization. So TMC in organic solvent, MPD in water solvent. So it goes to the polymerization and it creates the polyamide layer. And then on the active layer, and this is the support layer, polysulfone sulfonate, then try to also put polyester nonwoven specification because of the thickness, air permeability, homogeneity to stand the overall high pressure of the RO applied. So functionality, seawater, wastewater, it goes to active layer, and then support layer, and then this is the nonwoven layer, and then we produce the pure water. So you can see the very detailed polyamide layer is 0.1 micrometer. Polysulfone layer is 40 to 60 nanometer. Nonwoven layer is 100 micrometer, and it creates the water permeate from this active layer and then goes to desalinated water. So if you look at the more detail polysulfone polyamide layer, so let's see, this is the polysulfone layer, this is the polyamide. So you can see some belly rich type of the polyamide layer will be produced when you utilize the polymerization of MPD and TMC. And then this can be a nano size, almost when you have a water molecule around 0.3 to 0.4 nanometer. And then sodium chloride is around 0.6 nanometer size. So you have to separate sodium chloride and water. So which means this polyamide in terms of size is about 0.5 or 0.6 nanometer, which will separate the water from sodium chloride. So this is the future membranes. This microfiltration ultrapure RO membrane can be utilized for more membrane for post-treatment, and then hollow fiber also can be utilized, And also this is the carbon nanotube thin-film composite. Also aquaporin membrane can be aligned on the active layer as well as support layer to improve the overall performance of our membrane. Also, you can see that this is aquaporin membrane and the water molecule only selectively pass through, and this is the graphene membrane can play a role to improve the overall permeability of reverse osmosis. In 2021, the Kulf et al. From the Pennsylvania State University and the University of Texas, so they published one RO membrane paper in Science. In particular, they focused on water transfer. They mentioned that biological membranes can achieve remarkable high permeabilities while maintaining ideal selectivities by relying on well-defined internal nanoscale structures in the form of membrane proteins. Here, they apply such design strategies to desalination membrane. So you can see a lot of water channel from this membrane active layer. A series of polyamide desalination membrane which was synthesized in waste industrial scale manufacturing line and then buried in processing conditions, but retain the similar chemical composition, show the increasing water permeability and active layer thickness with constant sodium chloride selectivity. Transmission electron microscope measurement, which is the cover figures in this issue, enable them to determine the nanoscale three-dimensional polyamide density maps and then predict water permeability with zero adjustable parameters. Density fluctuations are detrimental to water transport, which makes a systematic control over nanoscale polyamide inhomogeneity a key route to maximizing water permeability without sacrificing the water selectivity in desalination membrane. They outline how keeping the density of membrane consistent is more important than the thickness of the membrane itself. So this can improve the water cleaning techniques where minerals are caught and removed by a membrane through the use of pressure. So in this membrane characteristic, they emphasize this: if we can control the density of membrane consistent, so 30 to 40% more efficient water permeability can be produced. So we can also consider in the future how we can control this density of the polyamide layer, which will be the one of the futuristic RO membrane. Also, we can improve module. So we have 8-inch and 40-inch, which is the most typical commercially available RO membrane. But nowadays, people make a bigger size, 16-inch RO module, high surface area. So this kind of membrane can produce the better water flux and then compactiveness of the overall membrane module. And also people nowadays develop the spacer using 3D printing and then they try to minimize the overall biofouling, membrane fouling on the top of the RO membrane. So that's the RO module. Also, people look at the bigger size, because bigger size of the module and then pressure vessel can improve the overall performance of your energy saving. That's the reason why people in the Veolia, they have generated the container size of pressure vessel, and then they can make more energy saving using their own developed technology. Also, we have internally staged the membrane design. So you can see how this ISD can produce the better optimization. So you have almost improved their overall internal stage. So if you see the pressure vessel in general, maybe 7 to 8 each module element can be allocated, and then nowadays all the module currently utilize the same quality of module. However, if we consider different internally staged design, so we have a different orange color, green color, and then this module can be designed as a different quality and then performance level of the RO module, so that we can improve the overall water quality as well as the specific energy consumption. So if you see this in front part, so there are many water fouling is coming through this membrane, and therefore we utilize the very high rejection RO membrane module, and then most of organics and then the contaminant will be observed in this two module, and then less rejection RO module, and then most relaxed rejection, which means the high water flux can be allocated in this module. So they have a different rejection and then permeability, so that we can allocate different locations and we produce the better quality of water as well as the energy consumption. So you can see the high product water quality in terms of what's the phase and ISD combination and SWRO recovery and average flux and the application. So you can see how it can be utilized. Also nowadays the ROSA, the reverse osmosis system analysis program, which is called Wave software, and this will create the more ISD design using the simulation. So we can also look at the simulation program to achieve this ISD process. So RO can achieve the different way of the overall performance, which will save your energy. So let's look at the pretreatment. The 0.4 kilowatt hour per cubic meter, how much we can save. So this is the one of the most typical pretreatment process. Conventional, which means the dual media filtration or center filtration or anthracite filtration, and advanced pretreatment is ultrafiltration. So considering their capital cost around 0.2 to 0.23, then O&M cost energy cost, chemical cost for the cleaning, and then total cost. So in fact, total cost $0.51 for cubic meter using dual media filtration pretreatment and ultrafiltration pretreatment. 0.52 kilowatt hour, $0.52 per cubic meter. So in Australia, so we are very fortunate. We have two desalination plants in Perth, Western Australia. So Perth desalination plant, and then down to 100 kilometers. So we have Southern desalination plant. So we have a different pretreatment process. Perth desalination plant was made in 1995. That's the reason why they are utilizing conventional pretreatment. So this Southern desalination plant was developed much later than this Perth desalinations, so that they have operated the advanced water filtration, ultrafiltration. So their water quality almost similar, and then they compare the overall pretreatment performance, and they believe the ultrafiltration is very much consistent operational cost, operational evaluation for RO, because UF is a very straightforward molecular size of the pore, and then all the contaminant can be removed. That's the reason why they have a relatively very consistent RO operation when you utilize the ultrafiltration pretreatment. On the other hand, Perth desalination plant sand filter, this is micrometer size of the pore. That's the reason why. So depending on your water quality, so they will produce the different quality of your pretreatment permeate, which is the RO feed water. So it's not consistent, therefore their RO performance is more fluctuating compared to the Southern desalination plant. So that's the overall. They have impression for your ultrafiltration, pretreatment, and dual media filtration. So depending on your water quality, you can select your pretreatment process. Also nowadays, the people look at how can save your energy using gravity-driven pretreatment. The seawater overall turbidity is relatively very low and then clean, so that we can operate our ultrafiltration or microfiltration using gravity-driven pretreatment, and we can save energy from 0.4 kilowatt hour per cubic meter to 0.01 kilowatt hour per cubic meter when you use the gravity, because we don't use pump, so we just use gravity as a small amount of pumping energy consumption, so that you can save a lot of energy using gravity-driven pretreatment. And for the osmosis RO hybrid system, so for RO hybrid, Desalination Research Center developed this technology with pilot level of scale, and wastewater very low salinity, seawater is the high salinity. So you have a different osmotic pressure, which you will get more high osmotic pressure will pass through your water molecule using the semi-permeable FO membrane, and then this reduced osmotic pressure can go to the reverse osmosis process and then continuously circulated, and we have less salinity will achieve the less energy consumption for your reverse osmosis process. So that this process does not require draw solution recovery and dilution of seawater using treated wastewater effluent by forward osmosis, reduction in the RO membrane fouling. Also, we can achieve the second barrier for high quality permeability. So we have also published this process for membrane module configuration for osmotic dilution of seawater by RO hybrid system. So if you want to further detail, so please you can find our publication. So this FOHC helium industry, they successfully developed 100 cubic meter per day, 1000 cubic meter per day, and then they found out around 30% of energy consumption can be saved when you utilize the wastewater and then seawater for RO hybrid system. So you can see the old pilot operation system using commercial one, and then different spiral round Apple module operation. What's the average water flux when you use the osmotic pressure of seawater, wastewater? You produce around 25 NMH, and then first element, second element, and then last element, which are around 12.5 NMH water flux, which is the optimized condition of our overall average flux, which can give a better operation. So that's the pre-treatment. So last but not least, post-treatment. Although the overall energy distribution is relatively small, 0.3 kilowatt hour per cubic meter, still around 0.1 kilowatt hour for cubic meter saving will save a lot of cost. That's the reason why we look at the kind of potential. So one is the pressure retarded osmosis. So which means this pressure retarded osmosis can be utilized as one of the recovery device as well as the energy production. So this was discovered 1970, and then first demonstration of pressure retarded osmosis, Statkraft Energy Company in Norway. So they demonstrate their technology 1 watt per 1 square meter of membrane can be produced. So at the time, the energy consumption production was very low. That's the reason why the Megaton project Japan, they successfully developed the CTA hollow fiber membrane through Megaton project, 10 watt for 1 square meter of membrane module. And then Korean project, global membrane distillation valuable product project, they also demonstrate the Toray simping composite spiral round module. So they found 15 watt per square meter energy can be produced. And then this is the also Singapore, they want to extend their opportunity for the future using hollow fiber PRO membrane. So this is the overall PRO activity. So it can be combined together with the reverse osmosis pretreatment. RO brine has a very high salinity. Also, the split partial single pass can be utilized. So this is the one of the new techniques we can utilize. So what we can do is that, so this is single pass, so you don't want to use second pass, but you have to achieve your overall energy consumption and then water quality. So what you can control, the seawater goes to the your pressure vessel and then pass through first module, second module, third module, and then they collect the permeate. But you can split within the your one pressure vessel. So you have a collect your permeate at the end of your RO module and collect and then goes to the your feed water side, which means this seawater will keep increasing your salinity, so which means you have permeate quality is very high salinity, and therefore if you mix with the front module, so your overall water quality is not as good as your initially collected your module permeate. That's the reason why you completely block your permeate at the end of your two module and then goes to the your feed side, which will reduce the overall osmotic pressure, so energy can be reduced for low osmotic pressure, and then your water quality can be improved. So this uh, has impact for osmotic dilution, lower pressure, purer permeability, permeate, uniform flux, and single pass reverse osmosis, which means you don't need second pass, which can reduce the capital cost. So that this SSP RO configuration can save 0.4 kilowatt hour cubic meter can be saved from this process. Also, CDI, capacitive deionization, can be utilized. So first pass, second pass, you have a very good quality of water quality, but still this permeate is high salinity. That's the reason why the commercial membrane utilized the RO pressure, the second part, so that you can achieve your better water quality using this second pass. But we can replace this second RO pass with MCDI membrane, which will have more energy saving. So energy consumption, so we compare the what's the different feed water after first pass, and then energy consumption of 0.175 and 0.223 kilowatt hour cubic meter is less than 0.35 kilowatt hour cubic meter currently used in pulse desalination, translates to an average saving of 60 to 80,000 Australian dollar per day in energy cost can be saved using this CDI process. Also, one company nowadays they have developed artificial intelligence can operate the reverse osmosis, which can save 20% of the OPEX. So Sinota, this is the Canadian company. So what they are doing is that they try to utilize the machine learning and then optimization of RO process and standard mathematics can be incorporated. So this is their concept. So you have a very high pressure pump, push it through your RO element, and then this element, after your water desalinated, and then goes to the RO brine. The pressure exchange will be applied, and then it goes to the boost pump, which called also balance pump. so that you have 1, 2, 3 pressure related unit for your one RO module element. So they utilize the machine learning when they have to optimize the high pressure pump, booster pump, pressure exchanger. Then based on that, they utilize the microservices. So SCADA system, cloud, infra, Docker, auto testing method. Also, they have main high pressure pump, and then their own train make a bigger size, and then they can save the 20%. So AI meets RO to save the overall OPEX cost. And your brine has a lot of mineral from seawater. So if you see the radium and some other valuable rare earth compound can be harvested. So resource recovery from RO brine is the additional value you can give for seawater desalination. In particular, our group has been worked on the radium recovery, almost 6 milligram per liter of radium concentration in our brine, and then we have developed some radium selective material can achieve the overall radium recovery. So we have published the radium recovery using electrochemical capturing system. So if you're interested to watch the resource recovery from seawater brine, so you can study for that. And last section is the future, which is unpredictable for reverse osmosis. So let me summarize my talk today. So we discussed about what's the energy saving, how much we can save. So this is the very typical RO energy consumption pre-treatment, reverse osmosis post-treatment. So total 3.9 kilowatt hour per cubic meter. So when you apply membrane IST spacer, you can achieve 20 to 40% saving overall, which will have a 3.1 kilowatt hour per cubic meter. FORO 20%, 25% saving. Gravity ultrafiltration 0.101, and then FORO hybrid system, PRO hybrid system 60%, 25%. Also, artificial intelligence, machine learning can save 20% of your RO energy saving, 3.12. So RO PRO process can be combined, 35% of overall energy saving. RO CDI 50% of the post-treatment saving. Also, split partial single pass can save around 90% of post-treatment, which is the 3.72 kilowatt hour per cubic meter. So if we combine all advanced technologies, we can save more than 65% of overall energy for seawater desalination. So in the future, so we need to consider whether we will focus more on membrane development, process development, module development, also configuration development, also post-treatment, pre-treatment will contribute overall energy saving. Let me summarize my talk. Desalination is a sustainable alternative water resource. 6 major desalination plants in Australia likely keep increasing in the future. Renewable energy with wind, The pretreatment is dual media filter mainly. However, ultrafiltration is also likely increasing because people believe this one has more sustained and then high quality of feed water through reverse osmosis. Energy efficient desalination becoming necessary and important to save our overall cost as well as the CO2 footprint. And the large amount of energy can be saved if integrated processes are hybridized and brine from the SWRO plant are treated through direct ocean discharge. However, reverse resource recovery will benefit the value additionally. So that's all about today's discussion. And if you want to know more about desalination, so you can join the 5th International Conference on Desalination using Membrane Technology. The MEMDES 2021 will be held in Shanghai 14 to 17 November 2021. So abstract deadline is June 2021. So please submit your abstract, and then I'm very happy to also discuss and then see you there. Also, you can join the International Desalination Association World Congress 2021 Sydney, November 7 to 11, organized by our university, New South Wales Government, New South Wales Events Australia. So you can have more opportunity to improve your knowledge and skills for desalination. Thank you for your attention.